So really great for everyone here. So for the discrete time Markov chain, and last time we introduced some notations, basic results, in particular we did classification. So discrete time Markov chain looks like right now is the time we can be what? Can be reducible and irreducible, or how we see reducible and irreducible. So basically, one thing we can do, we know each DTMC can be associated to a diagram or a directional graph. So if we look at that graph, if that graph is strongly connected, then what happened? Then the graph is strongly connected. In that case, the corresponding DTMC will be irreducible. Otherwise, we will reduce. That's one way. And also we see the graph is periodic versus so for which we count the what? The greatest common divisor among which we can come back. How we can't come back? We look into the transition matrix. So if you come back, you can start with I, you come back to I with positive probability. We call PII. The transition probability, you start with I, you come back to I. Now you count, say, suppose every 2 even steps you can come back. So now you can see P22 is positive, P44 is positive, P66 is positive. Now the GCD of all the steps, the greatest common divisor of all the steps will be GCD of 2, 4, 6, 8, etc. So we see will be 2. So in that case, the period will be 2. And aperiodic means in that case, you wouldn't find any integer that's bigger than 1. Then in that case, it will be aperiodic. Think about clock case. This is 12 digit. So now the period, if we have a DTMC with only 12 steps, so in that case, the period is 12. Right. And otherwise is aperiodic. And we also discussed what we mean by transient and recurrent. And roughly speaking, we have rigorous definition. We have a couple of ways we calculate this by theorem. But roughly speaking, so think about a node. You're on the graph. So what do we mean by on graph? A state, your DTMC we call state, or on the graph node is transient or recurrent. Recurrent means you are able to come back within finite amount of time. So if we use second or the Bragg-Cantley-Dingley, and so what that means infinite many times you can come back. You can revisit. You leave the state, you can come back in finite time. So in that case, that will be recurrent. Otherwise, it's transient, which means there's going to be a positive probability you're never going to come back. It's likely, how likely? The probability is positive. That among all the recurrent, suppose here is all the GTMC, and here is transient, here is recurrent. And within the recurrent, if not only you're able to return to where you start in finite time with positive probability, with probability 1, and also the mean of the average return time is finite. They're different. So the probability to come back is finite. Doesn't mean that every time you come back is finite. So if the every time we call mu I is finite, that's called positive recurrent. Otherwise, it's non-recurrent. So that's kind of the big picture we did last time. Okay, all right. So now let's see this. The basic theorem, we'll finish this. Basic limit theory. The basic theory. What this talk about, let's say we have a DTMC. And which is irreducible. Positive recurrent. This means the average recurrent time is finite. And of course, homogeneous, that's what we talk about all the time. If it's not homogeneous, one transition matrix, one step transition matrix is not sufficient to capture everything. You have to keep track of all those steps. So irreducible, positive recurrent, and homogeneous, let's say, with transition matrix, because homogeneous, we only need one single transition matrix. P, I'll use notation PJI. So here, we call PJI is the probability you go from I to J in one step, which is same as because of homogeneous. You start at I, one step you go to J. They're the same because homogeneous or stationary property. Anyway, so this is a transition matrix. We emphasize this. There are two, doesn't matter. There are two different ways people do this. They either do IJ, means transition from I to J. Then in that case, everything will be the transpose of what we talk about. All right, transition matrix this. Then what happened? Then we have first case. If the DTMC, let's say one state, all we need is one state. If state I is aperiodic. This is not periodic. This means DI is 1. In that case, what happened? The probability you start from any point, go to I as n goes to infinity. So this is different from this. What this means? Because this means in n step. This is start from 0, whatever you start, you go to the final state in n step. This means n step. This is saying, doesn't matter where I start, eventually I go to state I. What's the likelihood for this happen? How likely is this going to happen? And it turns out this is 1 over this. So this one is the mean return time to state I. And of course, a state would have any kind of period. Also, if it's periodic, has period, say D. is first this E is bigger than 1, okay? Then what happens? Now the limiting behavior, if start any state J, you go to I in n step as n goes to infinity. This is the asymptotic behavior. This will converges to D times mu I. Let's see what this is trying to tell us. Is the statement okay? Let's see what this is trying to tell us. This is saying I start with J. I go to I and take a close look, say the first case. What did you notice? You see something? This is independent. This asymptotic behavior. We have other color. This asymptotic behavior is independent where you start. No matter where you start, asymptotically, eventually, if you talk about final distribution towards one state, that's the final step towards one state. As n is getting larger, this is asymptotically, and it only depends on where you finally goes to, meaning the process forget. As you're doing this for a long run, the process forget, or DTMC, homogeneous DTMC, forget where it starts. So you start with anyone, and you will see the same thing. Of course, asymptotically, as your number step is getting larger and larger. Short time, that doesn't work. And second thing, this is the first observation. Second thing, let's look at this. What's this basically saying? This is saying in the long run. Big no. What does this say? This is the fraction time you start at J. Proportion of the fraction time you spend eventually at I. How likely that happen? Of the frequency of return to I. This is what? As this long run means, as you're doing this for a long time, asymptotically. Now you see this is inversely proportional to what? This is, I start with I. What's the average time I come back? Say, think about, if on average I come back every 2 days. So the frequency of returning is 1 over 2. Or the probability of returning is 1 over 2. Two things. For the limiting theory, first of all, it's independent of where you start. The process will simply forget where you start in the long run. That's the first thing. Second thing is, you see, this is the likelihood of returning eventually to one state. The frequency, how likely you're going to return, is what? Inversely proportional to the average time you need to come back. Does that make any sense? Just like if the period right now is 24 hours, what's the frequency? It's 1 over 24, right? So that's the frequency. And then this is a periodic case. It's not periodic. But if it's a periodic, then what happens? You're going to have D multiplier. Here is not very accurate. I should write this. Because what? If it's D periodic state I, eventually when you come back to I, the state, what happened? You have to step, your steps is D, 2D, 3D, and KD, and ND. Because it's periodic, right? So when you talk about N, and indeed you can replace this by that. What that means, and still the same thing, the frequency, how likely I'm going to return to one state is still 1 over mu II. But among all the D steps, because D step is a cycle, among all the D steps, only one step is admissible. So you divide the whole thing by 1 over D. So that's why you see this. Because dense, you are not going to more focus on every D step, not every step. So that's the intuition. And the proof is pretty long, so I'll put the reference right here. And the more involved, actually, we'll need more background to talk about the proof of this. So let me put the reference. Let's see. And England. To which book? Here's the reference. Carmen and Taylor. It's pretty old book, probably before everyone was born. 1975. Our first course is the stochastic process. This is the name of the book. And it's 1975. Okay, here's the reference. Hope you get the intuition. There are two key points about the asymptotical limit. The neglect. And second thing is, this likelihood is eventually look like this. If you know, this is where you need positive recurrence, because this will become, every return time will become finite. That everything makes sense. All right, clean this. Since we talked about this, now we're ready to talk about, remember, we talked a lot in the first part of this course, a lot about the long-time behavior for OD. So, and in some cases, that's basically something called equilibrium, right? So what's the equilibrium? That's not the right word. We will see the right word in a second of DTLC. Meaning the long-time behavior, how things distributed. So let's see, motivating example. For instance, so here, I simplify the clock. I only do 6. That's too much. So I have a weird clock, which only have 6 numbers. So here's the clock with 6 numbers. We can only do 12. Then you will see larger transition matrix, the same thing. So I assume start from anyone. The probability you do counterclockwise. So you can move counterclockwise with 1/3 probability, and clockwise, sorry, this is clockwise 1/3, counterclockwise 1/3, and stay at the same place 1/3. You do this for each of the steps. So basically what's this is saying, let's say Xn define the number on the clock in your n step. And now by definition, we can see the transition matrix is what? Here is the transition matrix. So you have 1/3 probability state at zero state. Here's 0, 1, 2, 3, 4, 5. And 1/3 probability move clockwise. And here's 1/3 probability counterclockwise. You're going to see, okay, the column A, stay here, 1/3 here, and there's a 1/3 here. There's 1/3. The column sum must be what? Remember that, right? This is start at 0. You can go to any other state. Stay at the same place, go to state 1, 2, 3, all the way up to 5. And all the other we didn't fill in there 0. So the column sum must be what? Must be 1, right? So you start with any state, and when you exhaust all the possibility, the summation must be 1. And here is for state 1, here's for state 2. So of course there's 1/3 below those. So far so good. That's a transition. As long as you see this, you can write it up, right? As long as you see this, you can write it up. Yes, 林老师.
0, 5.
This is 0 to 0. This is 0 to 1. This is 0 to 5. And all the rest, whatever the position spot we didn't fill in, there are zeros.
0, 5 to 0.
Yeah, there is things like that. So each of the step, they're similar on the clock. So I have equally likely probability turn clockwise, counterclockwise, stay at the same place, 1/3 each. So you can imagine that's basically is a tridiagonal. Oh, not really. There are 2 more things here, right? As long as you see this, you can write it up, and you can do 12, whatever. But now I want to give you the intuition. So the question is, suppose initially, first step, I just randomly pick one. I start here. And I want to ask, in the long run, this is not transition probability. This is not n-step transition. N-step transition is here. This is what asymptotically where you are. Basically, I'm asking you here. Initially, I know where I am. I'm at spot 2 on the clock. I ask you if I cover my eyes and just like a drunk person, I randomly walk, say do 10,000, really loud, 10,000 steps. Can you imagine where I potentially could be? Is the question clear? 是说现在我站在表盘上，或者是站在一个 circle 上，我从任何 spot 不是一般性，我就说是2 ，OK， 我从2那点开始，然后呢，我现在因为 cover 我的 eye， 就是说我走的时候只有3种可能，就是说在下一个 step 我可能没有 move，stay 在原点，还有是什么？我有1/3的概率都是even的哈，这个走这边的我不知道这是你们的 clockwise， 然后 counter clockwise， 对吧？对，我的问题是说，如果走很久很久 ，Can you tell me or can you guess very likely where I'm going to be? That's the question. 我们不知道这个，我们会算的，把它写成小 p， 看这样会不会很？我们会算。如果没有 intuition 是慢慢需要时间的。我们这个现在讲的太时间比较短。那你看第一步 P1 是什么？这个是说什么 ？What is telling us? This is saying initially P0 is what? How many states? We have 6 states. Only 6 days on the clock. Where we are? We're at 2, 3, 4, 5. This is initial distribution. Because initially you tell me I'm at state 2, right? So with probability 1. I'm not starting at any other place. That's where I start right now. I'm just saying that. So P1 is what? P1 is after one step transition. Right? We iterate. Right? So let's see. So I hope I have it out somewhere. So now you see here's the result. This is the first step. Now you see instead I more concentrated where I start and likelihood actually spreading up. This is saying I have a 0 likelihood because only one step. It's not possible you go beyond, right? I have 1/3 probability. That's exactly right. That's exactly right. And clockwise, counterclockwise, 1/3 probability state. Okay, so now let's see next step. You can do those, repeat those game. This is again, capital P is the transition probability. You apply this matrix, do matrix multiplication. So and basically, so we can keep doing this. We can write this up. So what I want you guys, I cover your eyes, nothing you can see. All the possible things you are staying on the clock. Can you imagine if you do this for a long run, say by the end of the day, where are you likely to be? Because the likelihood you do each change is the same. So you can imagine, can you guess? 我们可能会在哪呢？肯定不是一个固定的位置，对不对？那你会如果不是固定的位置 how are we going to talk about that? How likely I'm going to be in state 0, state 1, and state 5? You're going to talk about distribution. This is saying after one step, how likely I'm going to stay each of the state. This is after 2 steps, how likely I'm going to stay each of the place. So if you do this, now you see one more time. I think I have that. Hope now you can view. I'll write 27 all the time so you can see you can add it up to U1. You only have 2 states. And now you see, we only did 3 steps, 3 steps, 3 iterations. Did you notice anything? Before it's very concentrated where you start. And still, right? Now you see things spreading out, right? 猜猜看。因为就是 equally likely to do anything. 你们有没有听过一个 distribution 叫 uniform distribution？ 那就是说，如果必须得是 long run， 对吧 ？Asymptotically. So eventually you can be on any digit, any number, any state on the clock with the same likelihood. So what that means? Bless you. If it's equally likely, you have only 6 possibilities. What's the probability you eventually stay at any one of them? It's 1 out of 6. 所以每个概率都是1/6嘛，是 uniform。那这个是哪来的？这个就叫它的 stationary distribution of the stochastic process of the GTMC。就是 long time behavior， 就像我们研究不管 ODE、PDE， 我们做那个 long time asymptotic behavior， 对吧？那是 time， 我们现在是 discrete time， 所以你只有 step， 对不对 ？discrete step。但当 n sufficient large, you talk about what happened. This is what happened. Okay, all right. 那我们现在来看一下，stationary。这个不只是 DTMC， 整个 stochastic process 都是一样的，就是它所谓的 long time behavior。 equilibrium behavior. Not really equilibrium, a stationary probability distribution. Here's constant vector, that's called pi. Pi 0. Oh. It depends on how many states we have. Like that one, we only have 6 states, so right here you have 6 components. You may have countably many, so we put everything like the dot. If what? Think about dynamical system. We talk about the XDT autonomous. How we talk about long time behavior. As time goes to infinity, the equilibrium is what? Is where you settle. How you settle? It's not going to change because time is the only variable for ODE, right? So it's not changed over time. So this is going to be 0, or this is going to be 0. So that's the equilibrium, right? Now, what we're looking at, we're doing iteration, right? If we put in, if there exists a certain probability distribution, if we apply this operator, meaning the transition, what happened?
It change.
Yes, nothing changed. You stay. Mathematically, what that means? Exactly right. Yes. So that's exactly this, right? It's a stationary distribution. Once I'm in uniform distribution, 1, 6, 1, 6, all the uniform applied on this, you can easily see, and this is true. It's a fixed point. And not only that, this is the probability. You know, this is saying what? Pi, that vector is the eigenvector of the transition matrix associated with eigenvalue 1, right? Then what's the issue? What may be the issue? How many? Think about if you have eigendirection, even it's a simple eigenvalue, meaning the dimension of the corresponding eigenspace is 1. What's the potential problem? I can put 1, 6, 1, 6, 1, 6 for that example. I can always put 1, 1, 1, 1 as an example, right? It's still a fixed point because any scaling factor, you are still live at eigenspace or eigenvector direction. But this is the probability. What has to be satisfied? Has to be normalized. Which will be what?
Somewhat to 1.
Right. Is this okay? This is 1. This is a row vector, all consists of 1. This is normalized. Does that make sense? The eigenvector, even is a simple eigenvalue, you could have what? Infinite many options. But the probability can only be one of them, right? Which one? You normalize such that when you choose this and what? Not quite right. There's one thing is missing. I think I need this as well. You could add positive sign, you could add the other side. When you multiply -1, still true, right? I'm saying if pi is a fixed point, negative pi is also a fixed point. You multiply any constant, you have to guarantee this is what? Non-negative, and the summation of this is what? This is normalization condition. So that's how we define this. Back to the simple example, now we can see with what? Equal to Basically, when you solve this, you get 1, 1, 1, 1, then you normalize. You normalize, make sure the summation is 1. So you got this. So far, so good. So this is our deterministic analog of what? Equilibrium, or we call stationary state, right? We call steady state. Steady state for deterministic case. Now this case we call stationary distribution, probability distribution. You guys with me? Is this okay? Any questions? All right. Feel free to stop me if you have any questions. Also, you know, sometimes when I write and what I want and put over there may not be exactly right. So that's the point to check to see if you guys understand. Anyhow, and here is station distribution. Now, oh, I have a few warning. The station distribution, even if it exists, may not be unique. May not be unique. Let me give you a trivial example. Suppose the transition matrix is identity matrix. How many station distribution you can ever have? Oh, right, exactly. Suppose P, now I say finite state, otherwise it's go to countable many, right? Let's say 0 to n minus 1, you totally have n states. And for identity case, any, because the identity matrix, identity mapping, any, when you plug in any vector, that's a fixed point, right? But when you normalize, you're going to have, suppose you have totally n state, you have n stationary probability distribution. So what I'm trying to warn you is, even if there exists a station distribution, that may not be unique. Okay, all right. So far, so good? You with me? Okay, all right. So remember, then you probably ask, under what condition? It's just like you study ODPD, you will ask long-time behavior. There exists a unique, say, long-time, we call steady state solution. There exists a unique stationary probability distribution. Under what condition? There exists a unique probability. Here's the answer. Again, so we say this is what? A positively recurrent and irreducible. Reducing. And periodic BTMC. Then what happened? Then there exists a unique stationary probability distribution. Hi. Not only that, of course, you're going to see this. This is a fixed point transition matrix. This is related to the basic limit result we just erased. So I start with J, I, n step as n goes to infinity. Remember, the basic limit theory telling us this convergence to what? It's a frequency start from J, return to I, right? Is proportional or inversely proportional to 1 over the average time, return time. Not like period, like average return time. So that's your frequency, how likely you're going to return, right? But this one is telling us this equals what? That's exactly That's exactly what the ith component of that is data. So this, by basic theorem, we know this is true. This has to be for a periodic case. We talk about periodic, aperiodic, they're different, right? Remember? Periodic case, there is a D on the top because you only concentrate every one after these steps. So now, here's the quick thing, and to see this. So we saw three conditions. What's this? Irreducible, like identity matrix, is that reducible or irreducible? Can anyone tell us? What do you think? Identity matrix 是 reducible， 它有几个 block？ 假如说我说是 n by n 的，因为 in general 可能是 countable many 哈，我们就说 n by n 的，它有几个 reducible block？ 我们怎么看它的 reducibility？ 就是看它现在就是一个 up triangular matrix， 它有几个不可分解的小就是那个 subblock 对吧？它有 n 个，对不对？所以这个时候你就没办法 guarantee 什么，没办法 guarantee 对 uniqueness 非常好，所以那个 irreducibility 是 guarantee 唯一性的。那还有一个叫 positive recurrent 是 guarantee existence， 因为我们知道如果这个对的话 pi i 要等于 1 over mu ii， positive recurrent to guarantee average return time mu ii to be finite. Does that make sense? You guys with me? Aperiodic is just the simple relationship. Otherwise, you guys know what happened. This will be D over that, right? So what I'm saying, this is not necessary. So this is always true, but the limit, when this is aperiodic, that means that state has period 1. If the period is arbitrary positive integer, which is bigger than 1, this is just replaces by 0 that. So that's not the essential. The essential in things is irreducibility plus positive recurrence. So that's why we need to do classification first. So we can guarantee, like asymptotically, you are able to see the long time behavior. There exists a unique long time distribution. And the theorem not only telling us this exists and telling us how exactly that look like.
I have a double check.
Yeah.
So
all you need to check
the periodic, the condition of the periodic can be replaced by any period.
Yeah, this is not essential. So let's do this. Good question. So all you need is irreducible and positive recurrent. This guarantee uniqueness, this guarantee existence, uniqueness. That's all. There exists a unique stationary probability. And adding this, simply I want to show you this, how it look like. You can say if this is it depends on the state I, right? If the state I is periodic, this remains to be true, but this will be D over mu ii. That's all I say. But idea essentially the same. You don't need to check the period. If you want to check the period, and that will determine how eventually pi I look like. Will be 1 over mu ii if it's a periodic case. So let me redo this. I'll write the version. I think maybe I'll do this. So then furthermore, if BI is 1, a periodic case, then you have this. This actually equal to that. And second thing, if this is bigger than 1, say 2, 3, or whatever, then this is still true. Asymptotically, you convergence to the station distribution, but this will be right like that. Does that make sense? This is not essential. essential thing is this one and this one. So far, so good. So we know the answer. All right. And oh.然后大家可能会想，为什么我们做这个 DTMC？ 当然，它是一种 modeling 方式，对吧？还有什么？你想，这里很多人是做 spatial heterogeneity 的，你会做什么 ？spatial dispersal， 对不对？你可以把那个，比如说我现在这有是 six number on the graph， 你可以想成什么 ？six location, six city, whatever。然后这是它的 likelihood moving dispersal 吗？ To either of the state， 所以你可以做它的 long time distribution of the population。你可以做很多东西。Does that make any sense？ 还有就是，a couple days ago there was a 2-day workshop in Taipei, NCTS. So I think Professor Zhisheng Shuai talked about what? The asymptotic behavior. Of course, that's in a very special scenario. But he talked about some river network and the weighted sum of R0. So the idea sounds pretty simple. Of course, not always true. There's still conditions. So the point is, if I have 6 locations on my graph, within each of them, that's your ODE-PD model, whatever. That's your point model within those. You could be spatial dependent ODE-PD model. In each of them, you can calculate the corresponding something called basic reproduction number, right? So that's called the location R0. So you have R0, R01, R02, etc. Then you will ask me, what will be the R0 for the entire network? It turns out that R0 is approximately asymptotic to the leading order. And the dominant term is what? The weighted sum of location R0. And what's that weight? That weight basically is this pi. That makes sense, right? This is basically pi I telling us the fraction, how likely eventually I'm going to stay in this state. So it's a weighted sum of R0. What I'm saying is, whatever your ODE-PD model within each of them, you can do this, right? You got this R0. That has to be isolated or not. What I talk about is, locally you zoom in, here is the ODE-PD model, whatever. You get the R0, right? But now I ask you, here is my map in this location. Sorry, in this area, there are 6 regions I care about, right? Now I ask you, what's the network R0? Then it turns out that our network R0 can be a linear combination of location R0. So with some weight. What's the weight? Yeah. So let's see a quick example. This is coming from some real data. It's nothing like epidemiology. This is coming from ecology. So we say some sort of squirrel, 松鼠. Are native to a certain area. Area in Great Britain.不知道是不是叫土生土长的，就是本地的松鼠。对面的松鼠好像是灰色的，是 grey 的，对吧？加拿大是黑色的，美国跟这个很像，是灰色，但颜色可能是淡一点。Anyway， 他说这是土生土长的 native 的。 然后呢，这个呢，另外一个呢，这是 invasive，这是外来引入的，这不是当地的。然后我知道，就这个 area has four possible states. State one, the area occupied by the native squirrel only. By the breed, this is what invasive species. 这叫外来品种吧，或者是 both， 或者是 empty。所以你可以做 disease 很多啊，你分成不同的。然后 disease 有什么？就像 COVID-19 它有什么？对啊，它有 different strain。你可以说这是 strain 1 dominant 对吧 ？strain 2 dominant， 然后 co-infected no infection something like that. You the same thing. Okay. All right. 然后 we know. We know. 这是 coming from data, the transition matrix. 会是长得这样，我的天！哦。The estimate coming from data. Didn't copy anything from. Make sure the column sums. The transition matrix. What's the point? We want to determine the squirrel distribution. Over the long run. And the mean recurrent time. So how are we going to do the first one? This is simply saying here's the one step. Oh, no, I didn't tell you what's the initial distribution, right? Oh, no, I don't need. Why I don't need? For long-term behavior by the basic limit theory, initial. No matter where you start, it's just like what? This is say, I talk about OD system. I only have one global asymptotic stable fixed point. No matter where I start, no matter, it just matter of time. It doesn't matter number of iteration n. So somewhere n might be bigger, somewhere n might be quicker or smaller. Now I all converge to the station probability distribution. Now, so that's why initial doesn't matter. Talk about long time. It's the same. I know here's the situation. Here is the possible transition. What's the long time behavior? We all know we can solve the station distribution by finding the eigenvector of this, right? And of course, we need to normalize. So if we solve this, we need to normalize again, okay? We need to normalize. And also make sure each component is non-negative, right? I hope I have a solution somewhere. So everyone know how to solve this, right? Eigenvalue problem. you can do it, I think for this type of digit, you simply throw in the computer, right? And you calculate, then you normalize. Because the one they gave it to you may not be the one you want. Okay, then what we see is this is equal to 75% is the native species and 5% invasive species, both is 34%. And no squirrels, this is nice. It's 43%. How we did it, we simply solve this one and normalize. So far so good? This is good. This is saying 17% of the chance I'm going to eventually see the native one. And 5%, 5.6% going to see the invasive one, and both 1/3. Somebody they got 1/3 probably. The rest will be no squirrel. So that's good. Anyway, and here is the first part. The second part is what's the mean recurrent time? What that means? That means initially probably I very likely I stay with the location. I start with this, right? It's occupied by the native one. And then the mean recurrent time is what? Mu I is the average time take. I start with state 1. If I is 1, come back to state 1. Because the situation can change. So here it is right now. Now maybe green come over, they fight and take over the spot, the location, right? Oh, I don't know. This seems to me is very unlikely, and both live in the same area, right? And then here's no squirrel. Anyway, so what's this? When we did this, we have to do a lot of calculation to figure out what's the mean return time. Start with any state and come back. Let's do 1, 1. By the theorem we just talked about, we know this is equal to what? Of course, you have to check this is what? The finite state. Is this irreducible? Of course. All the spots are filled in by something, right? Irreducible, positive recurrent, because of finite state. Any finite irreducible Markov chain must be positive recurrent. 你没有无限个 state， 你总是可能有限回来的，对吧？然后这个还有一个是什么 ？a periodicity， 这个没有 cycle， 因为这个 graph 如果你画起来的话 ，1, 2, 3， 是 all to all connection，all to all。all to all， 我这个画的不好，每个和每个之间都应该有一个连线，是 all to all， 我只画了一个，是 all to all， 这还不对，这还有一个，还有个自己的，这是 probability 的自己的，对吧 ？OK， 是 all to all 的。Anyway， 那这个 by the limiting theorem， 我们知道它是什么？它是它，对不对？所以最开始，如果I start with 这个 location occupied by red squirrel, and on average how long I'm going to take to come back？ 这个数吗？5年。Likewise, you can do this. So I'm going to put this as doesn't make sense. So mu equal to mu I. So 5.865 17.我刚才说的是，这个是 irreducible finite Markov chain， 它一定可以 guarantee 我刚才说的任何一个条件。然后 by limiting theorem 我们就知道有这样的 relationship， 每个都是它对应的什么 stationary distribution 的 component 的 reciprocal。That's it. So far so good. 它能告诉我们，之前我们算这个费了好大劲。 Okay, so now Dr. Lin has a question. Why we need irreducible for DTMC to guarantee uniqueness? Let's just check out, for example. I'll pull something, okay? So I'm not talking about transition matrix. We're talking about transition matrix, probably something has to be 1/2, 1/2, like that, right? Okay, suppose it's a transition matrix. Now you are trying to solve the eigenvector associated with eigenvalue 1. His question is why we need irreducibility. Is that too strong? I think the quick answer is that's necessary, not even sufficient, also necessary. Because for each block, when you're doing this, you can take this one to be 1, 0, or I had 0, 1. They're all different distribution of this. This is just one block, right? This is another block. I need irreducibility to guarantee uniqueness, not only sufficient, actually that's necessary. Because each irreducible block, I can take 0 for the rest block. Suppose this is second block. I'm not talking about 1 digit, second block. And you can find this one, right? For the first block. And you can find that one for the second block. You can take anything you want. So irreducibility is necessary. Let's see where we are. So in just like the last simple example, we see we can find this one. This is the mean of first return time. And now the question is how to find this? IGLGI. Where did that go? What's this? This is the average time. So what's this? T, last time we defined, is called the first passage time. Start from I. First time, T counting how many steps or times it take, coming from I first time going to J. So this basically gives us a matrix. And here is the entry, the mean first passage time. Right now, for this matrix, we know how diagonal look like, if this is true. That's the diagonal, right? But in general, a diagonal is really unique. It's the first, is what? The average return time, because you start with I, you return to I. That's called return time. But when I is not equal to J, the off diagonal entries, what's the first passage time? So we're going to address that next. Is the question clear? And because before we had to calculate the corresponding probability and look at the infinite sum, it's such a long way to do it. Now I'm saying, I know how to find this, right? Is there a better way to find arbitrary first passage time, the average of first passage time? I talk about you have a matrix. Here is the GS entry is the average time you take, start from I first time return to J. Meaning how soon on average you can return, you can come to visit J. When I and J are same, we already know how to handle that. Now in general, how to do this. This is what we're going to do next. So far, so good? All right. Finite means a finite state. Here is a notation. A set of states. Let's call C of a BPMC. Is said to be closed. if it's impossible to leave. Mission impossible. Mathematical, what this means? So I have all the possible states for my DTMC, and here C is a subset. I'm saying C, this subset is closed. How to mathematical capture is not possible to leave C. What this means? So suppose here is C, here is the C complement. All the possible state minus C. What this means? This means start with any I. So I start with any state. Here's another state outside. It's not possible to leave, right? How we capture possible to leave? There is a positive probability you are going to do the transition from I to J, right? It's not possible. What this means? 0. So that's closed set. None of finite DMC. We see a set of state is closed. States C is closed. If and only if every state in the set is every state in C is recurrent. Recurrent. Second thing. If you have irreducible finite state function. Furthermore, if it's irreducible. Think about graph. Irreducible means what? Digraph. Any two nodes, you can find a path. You can move from one to the other one. That's called strongly connected, right? But in DTMC, what that means, you can go from any state I to another state J if it's irreducible. Of course, then the chain is positively recurrent. This one is stronger than recurrent. Recurrent just means the time you come back is finite with probability 1, almost surely. But this not only means that, not only the time finite come back, okay, the probability you come back in finite time is probability 1, also the average time is finite. And close, this makes sense. Think about what transient intuitively means, a transient state. Recurrent state means you can come back in finite time, right? Recurrent, you can come back in finite time. Think about periodic case, you can come back in finite time. Not periodic case, you can return. That's called recurrent. What's the opposite of recurrent? Transient. Transient means you may never be able to come back, right? You may never be able to come back. If it's close, what's close? It's kind of the information here. It's sort of, that's not very rigorous. It's like if you have that dynamical system that's possibly invariant. You state, yeah, this is just talk about probability, not very rigorous, but I think it's a reasonable analog. So you start here, you stay here, you're not possibly to leave, right? But now you talk about any state. As long as you can come back, it's not once you leave, you'll never be able to come back. Then all this kind of set, put it together, that will be a closed set. So that's what the theorem says. Now, our key question is we want to calculate, we want to learn how to compute, to calculate the mean. Let's write the whole thing, mean first passage time. Mean first passage time. So we talked about last time, first passage time is a big topic that can take the entire year, I think, to discuss this. For people doing stochastic process, doesn't matter your DTMC, any other process, they care a lot about first passage. Think about if you're interested, like say cancer case or disease invasion case, you will ask how likely the disease invasion is going to happen. Second thing, if that happens, meaning there is a positive probability that happen, you tell how likely, what's the probability. But if that happens, then you ask how soon can be captured by mean first passage time. It's just like you detect cancer, so through whatever the clinical check and the examination, now the doctors tell you and cancer is detected. Then you want to know how soon or how long you probably can stay alive, right? Things is similar, mean of first passage time, how soon. So I'm going to call M, it's mu Ji, mu Ji. So this is so now again in by the limited theory, we know how diagonal look like, but how about in general? So this is what we want to do now. So you guys want to see how to derive this, or you want to see the final result? It's up to you. I'll give you a minute and I'm erasing this. Think about it. You want to see how or why that happened, or you want to see how to do it directly? That's your choice.
So outline.
Oh, okay. Okay, let's try that. So let's say first passage time. You start with the I, and PID tell you the first time you come to visit J. This is the stochastic event. Every time you run the simulation and run the sample trial, this will be different. Sometimes could be sooner, sometimes maybe longer, sooner or quicker, sometimes maybe longer. And so let's say A, what should I call it? AK defined to be so state A can be accessible. We define those, what's accessible means you're able to visit them with positive probability. From state I. In many times, in one time shot. So let's do this. You are trying to calculate This is mu ij, sorry, mu ji. Every time, this is expected value, means the mean of the first patch that what's it every time you're going to do this. And of course, if you're lucky, you could possibly do this in one step. This is saying what? This is the event. I'm going to reach state J from where? From I in one time step. So that's this. And given this happen, you did this. You finish that. That's the most efficient when you did that in one step. This is how likely it will happen. And it's just like you discuss all the possibilities. Of course, in general, you probably won't be able to do this in one step. Since you were not able to do one step, you start from I, you reach some other state, say K, which is not J. So what's that? Let's see that this is just like a scenario discussion. This is called, in probability theory, that's called total probability law. Basically, talk about all the scenarios. You can go from I to J in one step, that's this. And you also can go to other state, which is not J. Then given you're doing this, you still want to know what's the every time you can go, sorry. Yeah, you can go from, not K. You can go from I to J, given the scenario. That's all the possibility, right? It's called total probability law. It simply discusses all the possibility. That's all the possible steps. I can go to J in one step, otherwise I go to some other things, right? So then what's this? If I'm able to go to J in one step, what's the expected time? Given that happened. You did it in one step, right? So the time is 1. Given this happened, that's 1, right? Given this happened, that's one step. You reach from J to I. 哦，我说对了吗 ？I to J. Yeah, I to J. Sorry, I to J. 这是 one step thing 嘛，所以这 every time 就是一，对不对？一步就到了嘛，对吧？然后不对的话，不对这个地方怎么办？这个地方怎么办？这个地方就像你们刚才说的，这个地方怎么处理？就这个地方怎么处理？哦，写到啥没选？我已经浪费了一个 I already waste one step of my time, right? Then what happened next? What happened next? 你 reach 哪儿了？现在是从 I 走到什么？走到什么？走到 K 了，对不对？你的 final thing 是你想 first time to reach 什么 ？K, that's it. 然后这是什么呢？这个就是 P 从 J to I 对吧 ？Transition probability, one step transition probability 就是 one step transition probability。哎，我有没有写对？是 J to 不是，是 I to J, one step reach J。这个是什么？这个是什么？这是 mu JK。这个是什么？这个是 one step 从哪儿到哪儿？从 I 到 K 嘛，对吧 ？That's it。如果你把它写成 matrix form， 这是什么 ？matrix form。Remember, we define M。应该我想写大写的 mu， 我把它写成 mu 就是 M 了。这是这个 matrix 是 M， 这个 equal to 这个是什么？这个是 all ones， 这个 matrix all ones 加上 M 点去 diagonal 对角线扣除，然后再乘以 P。好了， 给定任何一个 homogeneous DTMC，我们都知道它的 transition matrix， 这个是知道的。所以我们假如说我有是 finite state 是 n state 是 n by n 的，所以我有 n square unknown， 我就 solve 这个 equation， 这是 matrix 嘛，来 solve n square unknowns，the square equation n square unknowns。这就是我们怎么去 find the general mean of the first passage time by solving that. OK， 这个一哪来的？就是因为这是 P， 从 I 到 J， 这是从 I 到所有不等阶的，这加起来当然是一了。然后这个对角线要哪来的？这个本来几乎就是 M， 把对角线去掉嘛，就是把对角线去掉嘛，没有看出来？我说这是一，它俩加起来不就是一吗？因为 finite state column sum 是什么？是一，就是它嘛。把它去掉以后就剩它了，对不对？它就是所有的那个 mean first pass have matrix exclude 什么 diagonal， 对不对？把 diagonal 去掉嘛，这是它嘛。Anyway， 所以我们就得到这个 relationship， 那我们就可以去算。先来看一个例子。然后 last time we talk about a state can be absorption. Do we still remember what the absorption state means or absorbing state means? Absorbing 是什么？ Once you get there, you stay there forever. 那 a Markov chain 整个的 chain 也 could be absorbing. 这是 deterministic stochastic fundamental difference. If there exists at least one absorbing state. 你就想，我们做任何实际问题都要 touch boundary 嘛，对吧？那 boundary 对 stochastic case 我一定得加 boundary condition。就像我们做 PD， 我们 PD 有什么 non-non， 对吧？混合的 Robin， 就是你有不同的 directly， 你有不同的 boundary condition。那 stochastic 现在有问题是什么？你要避免你的 process go beyond the biological region。比如说，一般来说我们做的 biological process， 不管你是不是 epidemiology， 你其他也是这样，你不能是 become negative。那就有问题了。When you come to the boundary, what kind of boundary condition you have? 一种是 absorbing， 就直接上想是 absorbing boundary 什么呢？就相当于讲这是我的 boundary。我现在我撒了我的 glue， 这是 glue。一旦你碰触这个 boundary 一个球 ，whatever， 这是你 moving 的一个东西，它站到了这个 boundary， 它会怎么 ？Stay there forever。这就是 absorbing boundary 它的 intuition。OK， 我现在想说一个 Markov chain 也可以是 absorbing， 什么意思呢？我有一些 state 是 absorbing 的，不管我从哪儿开始 in the Markov chain。Eventually 我都会 end up here， 存在一个 absorbing state. Not only that, and it's possible to reach, to access the absorbing state from every other state. 不管你是做 stochastic differential equation 也有这个问题，那取决于你的实际问题。有时候人们会放 absorbing boundary， 那是什么 ？Once you touch 那个 extinction state， 你就 stay there， 这 process done 了，你不用再继续走了。这是有 fundamental difference between deterministic and stochastic。你想想，我们不管做的是加 Burson test 的 SIS 或 SIR epidemic， 我们都知道 R0 是一个什么 disease。Sharp disease threshold less or equal to 1 disease die out. However, then R0 bigger than 1 disease persists， 对吧？但是 for stochastic model, that's totally different. once you touch, no matter how big your R0 is, once you touch your absorbing boundary, say for instance, absorbing state or extinction state, you stay there. No more process. All right. Now assume, suppose my DTMC has K absorbing state. 所以这 transition matrix 可以写成就是 identity matrix K by K. Whatever something else, and here is T, here is all zeros. 怎么做到呢？这个 in general 是不对的，你要 permute reorder 你的 state， 你把那个 absorbing state 放在头 K 个。我说那个 absorbing state could be anywhere， 你 reorder 你的 index。 就可以做到，可以选头 first block 是 absorbing state， 这个是剩的 everything else。然后如果这个是 n by n 的，我们现在是 finite dimension， 这个 k by k 的这是一个 absorbing state， 剩下的 n 减 k by n 减 k 的这个，这是一 transit matrix 是什么呢？所有的 transit state 的 behavior 都 captured by T。那现在第一个 preliminary result 来了，这个 sub matrix。 That's a following problem. This is matrix multiplication. 换句话说，如果你 apply p n times n sufficient large 的时候，它的里面的这块就不见了。这一块 all distinguished。什么叫 transient？transient 就是你的 passing by state， 一旦你过去，你回不来了嘛。那最后去哪了？都去 absorbing state， 你有 k absorbing state。这个证明很简单，我把它 leave exercise for all the student， 只要用 matrix theory 就能证，用它的图就能证。哎，现在我们来看这个。Suppose without loss of generality， 我说我们的 DTMC has transition matrix， 这已经做了 permutation 了。就相当于是说 Jordan form， 你已经做了 quantity transformation， 把一个 matrix 放在 Jordan form， 就是 IK A0 T。这个 F 是 identity minus T inverse is said to be the fundamental， 这个不是 OD 的 fundamental matrix，the fundamental matrix of P。那么 so we will have the following result. 就是说这是 in general， 这当然不一定很 efficient， 这是 in general how to find the average of the mean first passage time. You can find all the entry right here. Use this one. 你把它如果写开，如果你这个 state DTMC 有 n 个 state， 这就是 n square equation， 有 n square unknowns。那现在是说，如果我有 absorbing state， 那我知道什么呢？ Eventually, the process will be absorbing to one of the absorbing state. Now, how soon, how fast that going to happen? So the mean is, every time until absorption is given by what? Business 这个 fundamental matrix 的 column 上，这理解很简单呢、看这个，这是什么？从 I 开始到所有的 j or possible j。这个是说 eventually 你要回到 absorbing state I， 你要花多少时间？那就是从这儿开始出发去 any other transit state， 你看的所有的时间把它加起来和，就是你需要的 final time 能 return 的，就是这个意思。对。好，我们现在可以 ，so for now I think we can see example。transition matrix。P。Determine the fundamental matrix。算是 What's the expected time until absorption？这是我们真正想看的，就是既然就为什么怎么知道absorption？特别简单，看 P transition matrix， 看哪一个 diagonal entry 是什么？是一。你看这里哪个 diagonal， 这是所有的 diagonal entry， 哪个是一？就它，这说明什么？这个 state 如果叫2的话，第二个 state 它是什么？它是 absorbing， 就是一旦从那出来，这你看它没有 probability go to other 嘛，只能 go to 自己，这是 absorbing state。那如果有 absorbing state， 但是它不在我们的这个 normal form 里，对吧？我们就 repermute， 比如说把1和2换一下，把1和2换一下 ，reorder 这个，我们就得到了这个，这是 reorder 以后的 transition matrix。那这个时候我们的 order 是什么呢？比如说我们是2、1、3、4，这是1、2、3、4。那它对应的 transition matrix 我叫 P hat 好了。就重新写一遍就对了。这是100。我们这个之一。这怎么做呢？就是说3、4不动，把1和2第一排和第二排换一下。Sorry, the first two column swap, the first two row swap. That's how you 对，只是 reorder 你的 index 嘛，这样我就写成它的 normal form。那根据刚才我们的 preliminary result， 我们知道 the transition matrix asymptotically 它会 converge to zero matrix， 因为所有的 state eventually 都会 absorb to absorbing state， one of the absorbing state， 所以这个时候它的 transition matrix 就剩下那个 block。那我们知道它的 fundamental matrix 它是 inverse 是什么呢？ 我就回去可以 check 一下，看我的 calculation 对不对？这是 fundamental matrix。那现在是 every time until absorption 是它的 column sum， 那就很简单了，就出来了。这个是什么？是2。这个是说什么呢？这是说，如果从 state 1开始 start on average， 我会 take 2 time unit to be absorbed by state 1。这个是说，如果从 state 3开始，我要 take 6 time unit， 然后 absorb to state 1。然后这个是第4个，这就是 mean the average of every time until absorption。Question？ 是什么意思呢？就是 on average it takes time solving state。就是说，当你做 epidemic model 的时候，这就是 fundamental difference。我们之前看过了，在我们考虑最简单的 the simplest SIS-SIR model，when R0 bigger than 1加 birth and death 哦，它 disease 都会 persist to go to positive steady state。可是等我们看 stochastic model 的时候，它会有 positive probability disease extinct。那如果是 finite case， 事实上 extinction probability 是 1， 就是说最后 eventually all the state 都会变成什么 extinction state， 不管你的 R0 是 bigger than 1还是 smaller than 1， 所以那是 fundamental difference。这例子我们可能需要一下，对，等一下，我去拿一下电脑。I'll be right back。去取一下我的电脑。等一下。So the anyone remote participant, can you guys see the projector? Is this large enough? I'll send you guys a file later, but just want to show you a quick example. This is a real DTMC model, and the point is they studying they want to understand the genetic inbreeding， 就是怎么繁衍后代。当有 mutation 的时候，这个 mutation 它会出现它的那个变种 variant form 叫 Alice。那现在就是说它会有什么呢？它会有2种，一种 mutated gene 它叫 capital A， 另一种叫 little a， 只是2种不同的，对。然后它这个 DTMC 就是讲 here's the mother, here's the parent, here's the offspring， 它这个breeding 的这个 process。现在就说，因为有什么呢？因为我们有2种不同的 genetic or Alice type， 有 capital A 和 little a， 所以说它的基本的基因组成会有什么？2个 capital A capital A， 或者是2个 little a， 或者是说一个 capital A 一个 little a， 这是基本的基因组成，对吧？ You guys with me？ 那 among all of those， 你 talk about the parents， 假如说这是 motherhood， 这是 fatherhood， 那他会从3个里任选2个，所以会有几种 ？3 choose 2， 会有6 states， 这是 all the possible 6 states。这是讲 father 和 mother 的 combination，3 choose 2， 会有6，对，从三个里选2个，对。那现在我就看第一个 case， 这个是 trivial case， 就是爸爸和妈妈 ，so both parents had the same genetic type。 然后如果是这样的话，这个下一代的这个 offspring breeding very simple. You have only one option. You can only have one type of offspring. 然后这个 probability 是什么？是 1。所以这个 P11 是 1， 就是他的 parents 是从 state 1生出的小孩还是 state 这个是吧？是 1。然后第二个 case 是说，一个 parents 是这样子的，另一个 parents 是这个。一个 parents 是这样的，另一个 parents 是这样的，是 different genetic type。那当然了，就他们俩都会有 1/2 probability contribute to this，然后 another half， 因为这个其中有一个 parents 有这个 genetic type， 会有 1/2 probability contribute to this。所以说它对应的是什么呢？我看它的 offspring， 它的 offspring 会有什么？会有，不会是 uniform 的了，会有这个，会有这个，会有这个，也会有这个，对吧？那我们就看它的 probability， 这个有 1/2 probability 产生这个，有 1/2 probability 产生，所以有1/4的 probability 会产生 first genetic type。Similar 有1/4的 probability 会产生 little aa genetic type， 而这个1/4只有1/4，所以这个是1/2。所以对应的这个这儿呢，不知道你们能不能看到我的 cursor？ 不能。所以它对应的这个 transition probability 从第二个 state 到1的话，这是1/4，到它到3的话，这个是1/4，但是到这两个是一个嘛，是1/2，这样清楚吗？然后你可以做这个 game for all of the possibilities. All I want to show you now, I have 6 different genetic states. 然后它对应的 transition matrix 就讲的这样。刚才我们一步步 derive 的，这个是1嘛 ，absorbing state。It turns out 这也是 absorbing state。我刚刚说了，看 diagonal entry， 看哪个是 1， 对不对？这是 absorbing state。这说明 capital A genetic type 和 little a genetic type， 这个叫 state， 我们叫我看有几个，6个，这个叫 first state， 这个叫 state 6， 它们俩都是 absorbing state。这是个 absorbing state， 这是个 absorbing state。如果你不想 reorder 的话，你就把它 leave it at here，because 这个现在已经是在它自己的 block 里了。那这个是什么 ？transition matrix。对，那个这一块就是 transition matrix T， 这个就是所谓的 A， 这就是所谓的 B， 它是 row vector， 可以吗？这一步步写出来，就根据刚才我们做的，刚才我不是做了我这个，对吧？每一步都可以写出来。对，我的 point 是下面的这个 classification， 我们之前做了很多了，已经做了蛮多的 example。我们知道第1个和第6个state， 它是 absorbing state， 它是自己一个 communication class， 它不 communicate with any other。然后中间的2、3、4、5。All the between state， 这是 one communication class， 所以我们现在有3个 communication class， 这没问题吧？对，然后这个1和6，那个太简单了，为什么 absorbing state 它的 mean return time 是1呀，走一步你就回来了 ，with probability 1嘛，所以它一定 positive recurrent。2、3、4、5是 transit。transit 是说什么？你出去了，你最后在这里不管转多少圈，你都 either go to 1。或者 go to 6。那现在我们来看对应的这个，我没有 reorder， 我现在就用原来的 matrix 求它的 fundamental matrix， 这是我们刚才的 definition， 把它求出来以后，找这个 every time until absorption， 我们就求出来是这个，对。然后那现在还有一个，就是用刚才这种方法，我们还可以求什么？我们还可以求 how likely eventual absorption to one of the state。我们现在有2个 absorption state， 如果只有一个的话，那就 probability 1 nothing to compute。就像刚才我们看到那个 trivial example， 所有的 state eventually 都 absorb to 2， 对吧？那是 probability 1。但是当你有 more 的时候，那你就问了，我有2个，就像2个吸引子 ，how likely 从这个中间出发 ，how likely 我会吸引到第一个 state 1， 或者 how likely 我吸引到最后一个 state 6。对 ，What's the probability？ 怎么算呢？ 这个 Pn 不是 transition matrix iterate n step 吗？因为它的 special structure 我们可以把它算出来，这两块不动 ，absorbing 的是 one 还是 state？ 这个 Tn 就 exactly T apply n times， 因为它的 structure， 但是 An 和 Bn 就有这样的 relationship， 那我把 n 就是 asymptotic go to infinity， 我就得出了这样的一个 vector。这个 vector 就是说我有4/3的概率从什么呢？我从 state 2出发，我会有 sub to 1啊。这个是说我如果从3、2、3、4、5，这是 2、3、4、5，这是 how likely I'm going to absorb to state 1，这是 how likely I'm going to absorb state 6。我想要这是个 real example， 非常简单的 model。就最开始那个文章恐怕是 Nature 上的。它就是 develop 一个 DTMC 的 model， 然后去研究它一些 property。So far so good, pretty simple and straightforward. I hope. Okay, all right. 我先 turn off this， 然后我们再看一下。Sorry， 我现在又不 display 了。我们再看一个例子，我想你是不是 DTMC SIS 去哪了？看一下是不是这个？看一下，像有是，我们一步一步来看，我没有写在黑板上，对，我们写在黑板上很不好看。怎么给你们看呢？这个是什么？我们先，对，我没有先讲，我们一会儿在黑板然后讲是什么。我考虑一个close population， 我说这 close 可不是 DTMC， 是 close population constant population size not vary over time， 就是 total population size conservatives。那现在每个 individual in the population 只有一个 state， 我有 n 个什么呢？我有 n 个，我现在写在这面，你们可以看得见吗？会不会太黑？可以看得见吗？没写在这边。写在这边，谢谢。close population of size S again 是什么？是 susceptible 的因素。我们然后是 healthy 还没有 become infected。I 是什么？是 infected。我现在当然了，在任何一个抵制 case 下，你最关心的是 infected population 它是怎么 change 的，对吧？它的 evolution。那我现在就让 xn the number of infected， 这个是 n step。time step。刚开始的时候可能有一个感染的，然后接下来会发生什么？再发生什么？就是这个是 xn reporting， 它是个 DTMC 还没有定义完的啊。然后这个 xn 呢，它会取什么样的值呢？最好的是说 nobody infected， 它就是 zero， 对吧？然后最多是多少 ？everyone infected。这现在是 finite state，OK， 是 discrete。然后我的 model assumption。第一个是只有2件事 ，SIS 大家还记得吗？这样换也行。 这是同一个东西，这是 infection， 对吧？然后这是 recovery， 这是 recovery， 有2个 event happen。那我既然是 keep track of what happened to I 嘛，就是我这里叫 xn。我现在第一个是说，如果 infection happen， 只有2个 event 可以 happen， 那这个 infection rate 是什么呢 ？If they are I infected individual。What's the probability that number of infected increased by 1? Number of infected increased by 1. Of course, in the next step. Next time step, one step. Next time step. Talk about the probability. 那既然它是从当前是 I， 它又变成什么 ？One more 是 I plus one， 就像 birth 似的，所以我说它叫 BI， 这只是个 notation， 就是 infection rate。infection probability 怎么定义的呢？这是 infection rate， 然后是什么呢？你们记不记得我们之前这个怎么做的 ？ds dt 是等于负的 beta。如果是有2种，我们取的是，我们来取 frequency dependent。S I， 以 I 的 D 是 beta S N I， 再减去伽马 I， 这个，这是我们之前做的 OD 对吧？这是 infection， 然后这是 recovery。那现在如果是 discrete case， 因为所有的 infection 就只能 take 这样的 value， 我们不可能有 anything continuous change in between。这里是 continuous change。那这个时候会有什么？这个 S 是什么 ？S 是 N 减 I 对吧？或者我们看这个，它有 conservation， 这个是什么？是 beta N 减 I N I 减伽马 I 对吧？一样啊。那这个是 N， 这是 I 对吧？是不是？这不是每个 unit time 你的 rate 乘以它的 time 现在是1嘛？每个 step size， 这是它的 probability given currently how many I infect individual， 你现在 infection happen， 它 increase by 1， 这是它对应的 probability， 对应的时间 delta t 是1嘛？所以这个没有了，对吧？然后类似的，类似的还有个 death， 不是 death recovery 我叫 DI， 因为 I 要减少一个，就是伽马 I， 对吧 ？recover probability 这不是 rate。它有乘以它的 rate 乘以它对应的时间，现在是1个 step， 所以是1啊，它对应的 probability。我们知道这个 model 是长得这样子的，这个清楚吗？给你任何一个 model， 不管多复杂，你都可以写得出来。No matter how complicated, you can do it. 你 just count how many possible transition。比如说你加 birth and death， 也许同学感兴趣的话，下午我们可以做。这个是我们现在做的是没有 birth and death， 我加了 birth and death， 你就把 birth and death 那2个 process 加进来就好了。birth 就是 I 到 I 加1 ，death 就是 I 到 I 减1，对吧？我现在讲的是这个 simple 的 SIL， 这个 OK 吗？没有 birth and death， 只是 SIS。So far so good。或者同学也可以下午做一下 SLR 的，好吧？好，那知道了这个，那你感兴趣的东西就很多了。它这个我们可以。这个是什么？要讲是 homogeneous mixing， 就是说 equally likely things happen， 对不对？然后它是一个 discrete time Markov chain， 那你就想知道它的什么？你想给你个 disease case， 你想知道什么？我想知道每走一个 step， 假设我的 time step 是 week 或者 day， 我比如说是 week， 我写 here is the currently infected situation， 我想知道下一周 next week。What's the average number infected？ 就是想知道 infected situation， 你可以求它 mean standard deviation 都会，对不对 ？You guys with me？ 那这是第一个你感兴趣，你还会感兴趣什么？你还会想知道什么？ 跟 OD 不一样的是什么 ？OD 是说 R0 大于disease SIS 它可能会 persist， 但是这不管你加不加那个 percent death， 只要是 stochastic 这个都不会，它最后 eventually disease 都会 extinct absorb to 哪个 zero state， 就是 extinction state， 因为那个 xn 等于 zero 的时候，它是什么 ？disease extinction state， 对不对 ？disease extinction state， 所以那你说如果 extinction happen， 你就想 how likely is going to happen？ 如果它 happen 了，你 figure out probability， 你还想知道 how fast？ 我们现在就来做这几件事情，然后来看一下这 code， 这 code 一会儿我会发给大家。很简单，我这个 toy 的，你这样子可以看到我的 transition matrix。我第一个问题是说，我想知道 what's the expected infected number of infected， 这怎么算？第一个问题是说，我想知道 on average 每一个 step 有多少人感染，怎么算？就想求它的 expected value 嘛，怎么算？你要想求给定一个 n。Sorry， 当 n is changing， 这是一个什么？这是一个链，对吧 ？Markov chain。但是 n fix 它是个 random variable， 怎么求一个 random variable 的 mean？ 最简单的方法，你知道它 distribution 就可以求它的 mean， 对不对？那它的 distribution 是什么呢？它的 distribution 是什么？它的 distribution。没有颜色了，这是刚开始的 distribution， 下一个是什么？是 apply transition matrix to initial， 对吧？然后你再继续做。这个小 p 是什么？大 P 是 transition matrix， 小 p 就是它的 distribution step 0、step 1、step 2， 你就一直做 iteration 就可以了。当你知道它的 distribution， 比如说我想求 expected value xn，sorry， 我现在没有黑板没有地方了，怎么算呢 ？expected value of xn 这个怎么算？这是它所有的 possible state， 现在有什么 0、1 up to n， 我叫 k。可以从0到 n， 这是它的 possible value， 再乘以它 how likely is going to happen， 是吧？我取这个它的 case component n 的 case component， 就是它对应的 probability， 这样清楚吗？你的 value 再乘以 how likely 对应的 value happen， 你把它加起来就是它的 mean。就像如果这是 uniform distribution， 所有的这个都是一样的话，就是相当于把所有的 possible value 加起来除以 n 嘛，因为所有的 weight 都是 1 over n， 对吧？但是它的 probability 就像我们刚才 clock 的情形下，每个 iteration 的 probability 不一定是 uniform 的，对吧？你不能把它加起来直接除以，要乘以它对应的 probability。它的 value 乘以 how likely is going to happen， 你把 added up 就是它的 mean， 这样可以吗？好。那我们看，这都是 set up。我这个 n 很小，所以我想让你看到那个 transition matrix 6 by 6。如果 n 是 5， 是 0 up to 5， 有6 states， 6 by 6。贝塔伽马是我随便取的，而且我们知道，如果是这种情形下 frequency based 的这个 modeling R0 不是贝塔除以伽马吗？所以你看，我现在故意取的是贝塔 0.2， 伽马 0.1， 除起来是2， 0.2除以 0.1 是2， R0 是大于1的，对。然后我们来做这个，这就是刚才定义的这个infection rate， 这个是 recover 不是 rate， 我是因为乘以 time 了，这是 probability， 就刚才我们定义的。为什么有 i+1 呢？因为 MATLAB 不喜欢 index 0嘛，所以我 shift everything by i+1， 从0开始的话就是1。只是个 shifting， 因为 MATLAB 没有 index 0， 对。然后下一个就是看那个 transition matrix P， 这个 P 长什么样？每个 state 你只有几种可能，每个 state 只有3种可能，你或者是 increase number infected by 1 due to infection， 就是这个。 你或者是 lose number infected by 1 I go to I minus 1 by recovery， 或者是什么 no change。那你看啊，这个是对应的什么？从哪儿呢？我们从这儿看，这是从 I 加again 那个加1和加2是因为它不喜欢 index 0， 我给 shift everything by 1。这是从当前的 state increase by 1， 这是 birth， 就是 infection happen。然后从当前的 state decrease by 1， 对吧？这是因为 recovery。那还有一种可能是 nothing happen， I stay at the same state， 既没有 infection 也没有 recovery， 在 next time step， 这是可能的。就是说现在。今天比如说5个人感染，明天还是5个人感染，暂且不动，就这个意思。那它的 probability 是什么？是1减去刚才所有发生的 infection probability， 然后likelihood for recovery， 你把都减掉以后，那个概率就是这个，这样清楚吗？所以当你写到 transition matrix， 一会儿我们在黑板上看，你会有一个大的一个什么？是一个 tri-diagonal matrix。diagonal 是不动的，从这个 state 出发你不动，下一个 step 不动。没有 transition 概率，然后往上走和往下走分别是 infection happen 加1，或者往下走减1 recovery happen， 上面是 recovery， 下面是 infection， 所以它是一个 tri-diagonal matrix， 可以吗？一会儿我们再把它，我现在就是定义这个 transition matrix， 因为我们一旦知道 transition matrix， 我现在只是随便取的，我说是什么 initially 我只有1个人感染了，那是什么？我有多少个 state n plus 1 state， 对吧？这是 state 1 state 2 state n plus 1， 所以 state 2， 这是为什么你看到那个是那个 p02 等于 1， 是 initial distribution， 只有1个人 infected。我现在所有的你看的 index 是 shift， 是因为 MATLAB 没有 index 0， 这只是个 technical 问题。OK， 然后你就做 iteration， 你看这就exactly 刚才咱们写的嘛，就是 current time distribution， 然后 apply transition matrix， 这是 next step probability distribution。一旦求出它了，我们就可以算什么 expected infection。来看一下哦 ，expected infection， 我这样写。是什么意思呢？是0乘以它0对应发生的概率，它第一个科目1乘以它1发生的概率，2乘以2发生的概率 ，n 乘以 n 发生的概率，那是一个。我们来看一下好了，还有一个 time to extinction， 把它放大一点啊。我现在画的是什么？这个 surface plot， 这 surface plot 这个是什么 ？number infected。我现在刚刚说了，我只有5个 population， 只有5个人，这是不可能的，对吧 ？Anyway， 很小，这是0、1、2一直到5，然后这个是你的 time step， 从0一直到 whatever you iterate， 然后我受它的是它所有对应的 probability distribution， 等于1的时候它有个 distribution all concentrated on 2。然后它会随着时间 iterate， 它的 probability distribution 会变。对，这是刚才我们画的那个，就是根据这个做 iteration， 每次 apply transition matrix， 这样可以吗 ？Questions？ 没 apply 一次，从你知道 initial 的 distribution， 没 apply 一次你就知道它的 distribution over time， 对吧？ probability， 你知道 probability distribution， 当然能算它的 mean 了。那刚才我们算的 mean， 我把这个关掉。刚算的 mean 去哪？这儿，这是 mean， 我把它放大一点哈。Let's zoom in。这个是什么？就最开始我们知道 how many people infected 1， 这个是说 over 1 times say 1 week， 大概 number infected 增加了1点，然后增加了1点，增加了1点，增加了1点。对，这是 average infection situation， 因为我们取的贝塔伽马不大，对吧？好，然后接下来还有什么呢？还有是说，这个是说，我想看，如果 我知道 extinction 一定会 happen 嘛，它是 with probability 1，我想知道 how soon 它 happen。那我们就用刚才我们说那个公式，就是刚才我们说的那个讲的那个算法。我知道 zero state 是 absorption state， 我把 first row first column delete， 它剩下的就是 transition matrix， 因为只有一个 absorbing state， 把那 absorbing state delete， 剩下的那个 sub matrix 就是 transition matrix。然后这是它对应的 fundamental matrix， 就是 identity 减去 t 的 inverse。我这么算只是说现在没必要，因为太小了。如果大的时候，就是 Gaussian elimination， 它的速度会快。然后这个是什么？这是 column sum matrix 的 column sum， 这是我们求的 time to extinction。我看我们有没有 print out 这个结果 somewhere。哎，我看不到了呢。Where is it？ 知道去哪了 ？Where is it？ 对，哎，我找不到了 ，sorry， 它去哪？哎，我没有看到这个 output。啊，这，sorry。这个就是说，如果我从一个人，最开始只有一个人是 infected，on average how many time unit take until absorption until disease extinction happen， 就是 29 time unit， 然后 etc。station 就是比如说我们已经知道了，这没什么好算，因为只有一个 absorbing state，probability 就是to absorption 就是 extinction 是 1。所以说这是它的 fundamental difference。我现在的 R0 事实上你可以变 R0， 你可以变那个 population size。然后用 DTMC model， 不管你那个 epidemic model， 我有一个 warning， 就是这个 this one and this one， 这不是 rate， 这是 probability。所以当你取这个的时候，你要 make sure 这个一定是要小于1的，如果大于就不 make any sense 了。那换句话说，这是我的 personal opinion， 我认为这个 DTMC 它不是很适合做刚才我们这个 population level 的，这是为什么我们目前只看到一个 example， 不管是 SIR 那个 epidemic model， 为什么呢？你要把你的 time step size， 它是什么意思？每一个 infection 都 happen at fixed time。你想想，我们的 infection 怎么会 happen at 一个 regular time？ 我们都是 irregular time。然后用这个做可以，怎么做呢？要把 step size delta t 缩小，怎么去体现呢？就在这个 parameter 里，这个 parameter 事实上是 transmission rate 乘以你的 time step。现在是因为我取的 step size 是1，就是你想 genetic mutation 或者是 offspring generation， 它都有一个固定的一个时间序列嘛，那个 time unit 你要把它乘进来。怎么看呢？就体现在对应的 parameter。这个 beta 事实上是 beta delta t， 这是 gamma delta t。我现在 delta t 是1，你要把你的 delta t 取得足够小，要确保它一定是 probability， 这个东西才会 make sense。但是我个人认为，它如果做 patch 做其他是可以的，直接 model 这种 population， 它不是一个很合适的 model。为什么呢？因为我们的 infection transmission recovery 它 happen 都是一个什么？ irregular time unit， 对不对？所以这是我们下午应该会讲的。现在看看大家有没有对这个有问题？有没有问题？
那我看一下那个
transition matrix，你说的是 transition matrix 是吧？
这个 component
对，等一下，你说 P 吗？哈，我等一下，我看看啊。这是 absorbing state， 对吧？对，然后其他没有了，这是其他的 1 2 3 4 5， 这个所有对应的 state， 就是说这个是 state at， 如果你只有一个 infected，probably state at infected 是 74%， 但是你可能会加1或减1，加1是 infection， 减1是 recovery， 所以你会看到一个 tri-diagonal 的一个 matrix。因为我现在的 events 很简单，只有2个 events 是什么 ？infection 和 recovery。当你有 more 的时候，它就会 wider 或者 bigger， 都是可以做的。
那
susceptible remain in the system at the time of accident.
What do you think? If you know how many infected, 这是个 closed population, so how many susceptible? It's n minus xn, right? I'm saying, if you know how many infected, the population is closed, is conserved. So the number susceptible will be n, total population size minus x.
I know. In this example, you
Oh.
can see how many susceptible remain.
Yeah, of course, you know XA, you know number susceptible, it's just n minus that.
Because what I am telling, because in the
Yeah.
deterministic model,
Right,
during the extinction of disease,
yeah,
almost susceptibles are born out.
yeah,
This is the most difficult.
Right.
question to treat.
yeah, so that's a,
How we observe here, there are sufficient amount of susceptibles in the system or not?
eventually, the punchline right here is because this zero state, meaning biological is extinction state, this is absorbing state. It could take long, it could take short. That's how long on average take to reach this state. So eventually with probability 1, you see this, the station distribution, that pi is 1, 0, 0, 0, 0. This is saying eventually all the state will go to absorbing or disease extinction state. So in other words, and S will be taking care of for SIS epidemic, S will take care of everything, super large. But this is different from deterministic case. I'm saying the deterministic case, you may sustain to something positive, we call endemic or something, right? We don't have that. Even you're adding birth and death, you're adding more complicated things because this boundary issue. Okay. All right. Any other questions? Excellent questions. Online folks, any questions from remote participants? Comments? 我希望大家清楚一点的是说，那个 deterministic stochastic 会有一些 essential difference。然后这也是说明了什么时候适用什么样的 model。就我们去做 model 的时候，什么时候 stochastic 会比较合适呢？ When the stochastic model, for instance, DTMC, later we're going to talk about CTMC, might be more appropriate. Think about that. When and say ODE model, when PDE model. ODE 和 PDE 的 fundamental difference, where they care about what? Spatial heterogeneity. 如果 you don't care, it's a point model, ODE is sufficient. 但是如果 compare to ODE to stochastic, 你要想一想 when or under what situation may be more appropriate one versus the other one. 我个人的理解是这样的 ，in my opinion， 就是说 disease 刚刚开始 start 的时候，只有几个人感染的时候，这个 stochastic process 或者 stochastic model probably will be more appropriate。但是如果当这个 disease 已经 launch 了，比如说它的 epidemic， 这个时候 talk about population level，ODE 可能是很好的一个 capture， 而且它可以给你一个很 quick 的一个 big picture， 你不用 run 很多的这个 simulation 去理解一个 phenomenon。我觉得是两个东西 put together， 这是我个人的认为。但是有一个 tricky 的问题，就是 when is the threshold？ What I'm saying is under what situation？ Say population sufficient large， 对吧？那是多 large 吗？你可以用 stochastic。After a while， 你 talk about long time behavior 的时候，你可能用 deterministic。那这个 threshold， 这是 problem by problem， 没有 fixed threshold。不知道我这样说清楚吗？ I'm talking about in the very beginning, the starting of the initiation of outbreak 或者 epidemic disease 的时候，一个 stochastic model 可能是会更 reasonable。But we will talk about homogeneous structure, whatever, say deterministic differential equation 可能会更好。为什么？它 tell you the average behavior of everything. Deterministic tell you the average. 你可以 quickly capture what's going to happen in the long run. 对，好，那我们现在大概还有10到15分钟，我们是要开始讲一点 DTMC 还是下午讲？你们决定。It's up to you guys. 我们现在要 switch the gear, talk about another talk. 这个是 discrete time marker chain. We're going to switch gear to talk about continuous time marker chain. Shall we start the definition? What do you think? It depends on you guys. 好，下午哈 ，OK. Let's do it in the afternoon. So you guys are going to have a longer break. I think we'll come back around 2-ish, 2 o'clock, right? To about, yeah, 2.5 hours. So I'll see you at 2. And in the afternoon, we're going to talk about continuous time marker chain. If you understand this well, I think probably we can move a little bit faster, hopefully, for continuous time. Anyway, that's all for this morning. So online folks, remote participants, are we okay? Any questions? If not, let's close the morning section. We'll continue our discussion at 2.